Conversion graphs. A conversion graph can be used to convert one quantity into another. The two quantities are in direct proportion, and so the graph will be a straight line, which will usually pass through the origin. A notable exception to this is the conversion graph between Celsius and Fahrenheit. Example 17. Use the conversion graph to draw a conversion between miles and kilometres. Now what we'll notice is that miles comes first, and the standard practice is whatever comes first is going to be in the x-axis, and whatever changes as a result of that is the y-axis. So we need to label the points. Obviously 0 miles is 0 kilometres, so it's going to go through the origin. 50 miles is 80 kilometres, and 100 miles is 160 kilometres. So if we join those points up and form a straight line, we get this shape. Now we can use the conversion graph to convert 80 miles into kilometres. So if we go to 80 miles and draw a line up from 80 miles to the graph, and then from the graph over to the kilometres, we will see that the approximation is 128 kilometres. And that's because each small square on the y-axis represents 4 kilometres, because there's 5 between 20, so there's going to be one square is 4 kilometres. To change 72 kilometres into miles, same idea, only this time we'll go from 72 kilometres, which is 2 squares short of 80. We go to the graph, and then we draw the line from where the graph hits it down. We'll see that it's in the middle of 40 and 50. So the answer there for part B is going to be 45 miles. And then for part C, 8 kilometres into miles. So we'll go 2 squares up and read across to the graph. And then from the graph, we'll draw the line down, and that's in the middle of the 0 to 10. So that means in part C, the answer is 5 miles. And in fact, this is the best conversion rate that we have, is that 5 miles is approximately equal to 8 kilometres, and that's something that really we should know. Example 18, use the graph to convert between kilograms and pounds. Again, kilograms is at the top of the table, so it's going to be the x-axis, and pounds is the corresponding thing that changes, so it's y. So 0, 0, if you've no kilograms, that's obviously going to be 0 pounds. 50 kilograms is 110, so that's in the middle. And 100 kilograms is 220, and then we can join those up with this straight line. And that's what we got. So then we can use the conversion graph to convert 70 kilograms into pounds. So we go from our 70 kilograms and we draw a line up to where it crosses the line, and then from the line across to the axis. And we can see we're 2 squares short of 160, so part A is going to be 152 pounds. Part B, we're trying to get 120 pounds into kilograms, so we draw a line from 120 to the conversion graph, and then from the conversion graph down. You can see we're halfway between 50 and 60, so the answer there for part B is going to be 55 kilograms. And then part C, we're going 10 kilograms, and we're converting that into pounds, so we go up from the 10. We're just slightly above the 20, so we're about half a square above the 20, so that's going to mean that the answer is 22 pounds. And this forms part of one of the most common conversions that we use. So we've just said that 10 kilograms is approximately equal to 22 pounds. So 1 kilogram then is approximately equal to 2.2 pounds, and that's the most common equivalency that we use. So in the notes we said that Celsius and Fahrenheit was one of the exceptions. So we're going to look at that. So 0 degrees C is 32 Fahrenheit. So that's going to be, here again, 1 small square is worth 4. So we're going to go 3 small squares up. 60 degrees is 140 Fahrenheit. And then 100 is 212. So we're going to go 3 squares above the 200 mark. And we can join those up. Now to convert 76 degrees C, we go to 76 degrees C, so that's going to be 3 squares after the 70, because each small square is worth 2 until we get to the line, and then go from the conversion, so that's halfway between. So we're going to say that for part A, the answer is 170 degrees Fahrenheit. Part B, 100 degrees Fahrenheit, so what we'll do is we'll go from 100 until the line, and then from the line down, and we can see that's 37 degrees C. Travel graphs. A distance time graph or travel graph can be used to represent a journey. It shows the distance travelled during a period of time. Time is always plotted along the horizontal axis, so I'm going to highlight that. And the distance travelled is plotted on the vertical axis, so distance is in the vertical. A journey will consist of several stages. Each stage is shown with a different line. The slope of the line indicates the speed at which the object is travelling. A steep line shows the object is travelling quickly. A less steep line means the object is travelling slowly. So just to make that really clear, if we had a steep line, that's travelling quick. If it's a shallow line, it's travelling slower. So this would be the fast line, and this would be the slow one. A horizontal line indicates that no distance has been travelled, in other words, the object has stopped. The speed at which the object is travelling can be calculated by reading from the graph the distance and then using the formula speed equals distance over time. So in physics, you might use different letters for things, but we quite often have a speed, distance, time triangle that we can use to work out the other. So if we want to work out speed, we cover it and we can see it's d over t. If we wanted to work out time, we can cover the time and it's going to be d over s. And if we want to work out the distance, it's going to be s times t. The other thing of note is that the average speed of a total journey is the total distance over the total time, including stopping times and everything else. So that's for the average speed. So example 20, the travel graph shows Anne's journey to her grandma's house. Describe her journey. So what we can say then is that Anne, for the first part, which is from 12 to 12:20, she's travelling at a constant speed. So constant speed from 12 to 12:20. Then from 12:20 to 12:40, she stopped. And then from 12:40 to 14:40, she's travelling with a constant slower speed than the original part of the journey. Anne's brother Ben left home half an hour later and travelled to the grandma's house at a constant speed of 15 kilometres per hour. So that means that Ben left home at 12:30. If he travelled at 15 kilometres per hour, that means at 1:30 he will be 15 kilometres, and then at 2:30 he will have travelled 30 kilometres. So we can join that up with a straight line, and that is going to be Ben's velocity or distance time graph. Now, I suppose if we were being really fussy about it, which we should be, we can see that Anne stops at her granny's house, which is 27.5 kilometres away. So really for Ben, we should do the same. We should make his graph finish at 27.5 kilometres. So we should reduce that line down to there. At what time does Ben pass Anne? So that's part C. And what we're looking at is then the point at which they meet. And we can see they meet at 2 o'clock or 1400 hours. Part D, how far away from home are they when Ben passes Anne? So that's going to be the vertical distance, and it's far from home. So they started from home and then they got to their granny's house. So it's this distance here, which we can see is 22.5 kilometres. Example 21, the graph shows the journeys of Claire and Dermot. Who travels farther? Well, if we look and see, Claire starts off 30 kilometres from Belfast, and then at 1:50 has arrived in Belfast, so that's a total distance of 30. Whereas Dermot starts from Belfast and then stops 20 kilometres away. So then we can say that Claire has travelled further because that's 30 kilometres. Dermot had travelled 20 kilometres. Calculate the average speed of which each of them is travelling. So what we know is that the average speed is the total distance over the total time. So for Claire, what we know is that her total distance is 30, and the time that she takes, because it's kilometres per hour, we need the distance or the time in hours. So 12 to 1 is 1 hour, and then we've got to 1:50, and 1 hour 50 is as a fraction of an hour, so it's 1 whole hour. 50 out of 60 minutes is 5/6. So then if we divide 30 by 1 and 5/6, we get 16.4 miles per hour to 1 decimal place. For Dermot, he travels 20 kilometres. Now he starts at 12:30 and ends at 2:30, so that's 2 hours he's been on the go for. So that's 10 miles per hour. Part C, at what time do they pass each other? Well, we can see that's the point where the two lines meet, and they pass each other at 1:30 or 13:30. And part D, who is further from their destination from where they pass? So what we can see is that Claire, at the point that they pass, is 10 miles from the destination, and Dermot is also 10 miles. So they both have 10 miles to go. Example 22, and I'm going to highlight some things as I go along here. So a bus begins its journey from Coleraine at 10 o'clock. It arrives at Port Stewart, which is 10 kilometres away, at 10:40. It stops there for 10 minutes and then continues a further 6 kilometres to Port Rush. It arrives at Port Rush at 11:50 and it stops for 10 minutes before returning to Coleraine without stopping. It arrives back in Coleraine at 12:40. So we need to draw a travel graph to show this information. So travel graph is always time on the x-axis and distance on the y. The journey starts at 10 a.m. and then what we'll do is we've got enough space to make each square worth 10. So then we'll have 10:30, 11, 11:30, 12 and 12:30. On the y-axis, we've got enough for, if we take each small square is 2 kilometers. And the distance is in kilometers. So let's trace this out. So it starts at 10, and then 10 kilometers away at 1040. So 1040 will mark in that they're 10 kilometers away. And we'll join that up with a straight line because it travels at a constant speed. Then it stops for 10 minutes. So there's going to be another horizontal line for 10 minutes. And then travels a further 6 kilometers and arrives in Port Russia at 11:50. So that's a rather slow part of the journey. There's another rest for 10 minutes. So that's going to be another horizontal line. And then it will return to 12:40. And it's a straight line. It's a constant speed. There's no stops. So there we've got our distance time graph drawn. So part B, was the bus travelling more quickly between Coleraine and Port Stewart or between Port Stewart and Portrush? So what we can see is that the first part of the journey it has a steeper line. So therefore the first part of the journey is going to be the quickest part. So between Coleraine and Port Stewart. Part C, how long does the return journey take? Well, it starts at 12 and ends at 12:40, so that's 40 minutes. Or 2/3 of an hour, because it's 40 minutes out of 60, which simplifies to 2/3. What was the average speed for the return journey? So speed is distance over time. So the distance is 16 kilometers. And because it's time, we're going to use that 2/3 of an hour. So we're going to divide 16 by 2/3, and we get 24 kilometers per hour. Now we could do that in terms of a ratio. So rather than doing 16 divided by 2/3, so we could say that it was 16 kilometers in 40 minutes. That means it would be 8 in 20, which means in 60 minutes, it would be 24 kilometers. And if you're traveling 24 kilometers in 60 minutes, that's 24 kilometers in an hour. What was the average speed for the outward journey? Well, the average speed, again, that's distance over time. So that is 16 kilometers, and it starts at 10 and arrives in Portrush at 11:50. So that means it's 1 hour and 50 minutes, which is 1 hour and 5/6 of an hour. So 50 minutes is 5/6 of an hour. So if we do 16 divided by 1 and 5/6, we get 8.73 kilometers per hour to 2 decimal places.